I thought we would never be able to finish recording so we could enjoy our pie.
I bit my tongue.
How'd you bite it?
No, not bite, bit.
What's the difference between bite and bit?
Well, a byte is 8 bits.
That really sounds like a job for level 314.
Welcome back, Coding Wizards. Today we start part 3 of our series on solving the genius square, where we've been learning some fundamental concepts in mathematics and computer science to help teach our computer how to solve this puzzle game. Now, if you're unfamiliar with the game or you missed the first 2 parts of the series, be sure to click the link to check out the playlist. And also make sure you stay tuned to the end because we'll be announcing a special giveaway that's particularly useful for young children stuck at home due to COVID-19. Be sure to pay special attention throughout the video for 2 Easter eggs regarding the mathematical constant pi for extra chances to win in the giveaway. And that's it for housekeeping. So without further ado, let's set up a few games and get started with part 3. So far, we have calculated that there are over 10 million unique Genius Square games possible. If you could set up and solve each game in just 1 minute, over 19 years would be required to complete them all. That makes this a perfect problem to solve with a computer. But even then, if we wrote a program that could set up and solve each game in just 1 second, it would still take 115 days of continuous processing to solve them all. When coding, it's often not enough to just solve a problem. We have to find ways to solve it efficiently. In computer science, we break down such efficient solutions into 2 major components: data structures and algorithms. Today, we'll be dealing with that first component. So, what are data structures? Simply put, they are how you organize, manage, and store the information representing whatever it is you're modeling. These structures are how we move from the real world into a simulated world running in the matrix. On your computer. Today, you're going to learn how to do that using the powers of 2. In everyday counting, we use what is called the decimal digits. The prefix deci means 10, and there are in fact 10 familiar digits ranging from 0 through 9. But what happens if we only use the first 2 digits, 0 and 1? What we are left with are the binary digits. Here, the prefix bi means 2, like in bicycle. We can shorten this term by removing the middle letters, creating a new word, bit. This word bit means a single binary digit. It is the basic unit of information in information theory, computer science, and digital communications. A single bit, represented by this box, can either have a value of 0, sometimes called false or off, or the bit can have a value of 1, true or on. So with a single bit, you can have at most 2 different values. What if we had 2 bits? Let's represent the different values in both binary, using zeros and ones, and in the decimal format you're more used to counting in, using all 10 digits. Okay, so we've counted to 3, but remember, we started at 0, so that's a total of 4 unique values with 2 bits. Before moving on, let's relabel the yellow value. We'll call them integers. This same bit pattern can be used to represent different quantities in the computer. Integer just means we are showing what the pattern of bits means in positive whole numbers. No fractions, no negative numbers. Okay, but we really want to be able to store more than 4 different values. The only way to do that is to add more bits. So let's double it again. 4 bits is called a nibble. Sometimes this value of 4 bits is written in hexadecimal notation. Hexa means 16, so we do this by using the familiar digits 0 through 9 plus the letters A through F to represent the additional 6 digits we need. Counting through the different options here, you will see we do in fact get 16 different values, 0 through 15 in decimal notation and 0 through F in hexadecimal. Let's double the number of bits in our computer again. 8 bits is known as a byte, and 1 byte can store 256 unique values. 8 bits to the byte became the standard due to its ability to store the full Latin alphabet in lower and uppercase, all the decimal digits 0 through 9, and the most commonly used punctuation. You may have heard of the standard which codifies these letters and these bit patterns, and it's called ASCII. And as you can see, with 8 bits, it does in fact count 0 to 255 or 0 to FF in hexadecimal. Let's take a look at understanding how we translate from binary to integer values. To do this, we first number the bits from 0 to 7, going from right to left. When all the bits are off, we have the value 0. Turning on the first bit, bit number 0, we get the value 1. Every time we shift that bit over to the left one place, we multiply by 2. So shifting the bit over to bit 1, the integer value becomes 2. Shifting again, the value is 4. And again, we get 8. If we shift the bit to the left 2 times, we multiply the value by 2 times 2, or 4. So here we jump from 8 to 32 if we shift twice. A more direct way to figure out what any on bit is equal to is to realize that the bit values are the powers of 2. This means that the value of bit 5 is 2 to the 5th power, or 2 times 2 times 2 times 2 times 2 equals 32. What happens if we also turn on bit 1 now? To determine this value as a base 10, aka decimal integer, we simply calculate 2 to the 5th power plus 2 to the 1st power. That gives us 32 plus 2 equals 34. Okay, what about this pattern of bits? Go ahead and pause the video if you want to try to figure it out on your own. Were you able to solve it? You should have gotten 2 to the 7th plus 2 to the 6th plus 2 to the 3rd, or cubed, plus 2 to the 0th power. That equals 128 plus 64 plus 8 plus 1, remembering that any number to the 0th power is equal to 1. And that sum is equal to 201. Okay, 8-bit was a nice start, but for computers to be more useful, they have to be able to count higher than 255. Let's make a 16-bit computer by adding on another 8 bits. Now, if we add our new bits to the right here, we change our integer value because now we have 2 to the 15th plus 2 to the 14th plus 2 to the 11th plus 2 to the 8th, or 51,456. We can shift these bits all the way back down to the right. Each time we shift to the right, we are dividing by 2 until we get back down to 201. But these bits don't just have to represent integers or encode letters using ASCII. We can also use them to represent fractional numbers. In computer terminology, we call this floating point numbers. So what is this value in floating point? Well, it equals 3.140625. This bit pattern is as close to the mathematical constant pi as you can get using only 16-bit floating point. Note, this is not one of the 2 pi Easter eggs, but keep your eyes out for them. If we want to get even closer to pi, we have to move up to 32-bit computing. Here is the binary approximation using 4 bytes. This is known as single precision floating point, and we have pi accurate out to 6 decimal places now. Doubling our bits again gets us to the current gold standard for personal computers, 64 bits, where this binary representation gives us pi accurate to more than 15 decimal places. Bits are the heart of how computers represent the world, from integers to floating points, to photographs, and even to this very video you're watching right now. At the lowest level, it's all ones and zeros. So how can we apply this to help us solve the Genius Square? Using a bit field, which is a data structure made up of individual contiguous bits of computer memory. We do this by modeling each of the 36 squares in our game board as individual bits, numbered 0 to 35. If there is a peg in that square, we turn that bit on, and if there is no peg, that bit is off. Flattening the board so the bits are in the more familiar layout, we can see the binary representation, and by doing our math, we can see our board as a more familiar decimal integer is 1,208,615,568. We can efficiently represent any board now with any number of pegs as a unique bit field and refer to that bit field as its integer representation. Here we see our boards from the start of the video and their bit field equivalent. But we don't have to stop with the pegs. Even the positions of our game pieces will be represented by bit fields. Now, let's jump into Excel or your favorite spreadsheet program and make a prototype of our game board bit field. Excel is a great tool to use to quickly prototype solution designs for coding projects. I've set up a few cells here to mimic our Genius Square game board. This first one I will set up to use the square numbers. I'll just copy these numbers across and fill in the series. So now our squares are numbered 0 to 35. We have 36 squares. This second board here, I will set a formula and I will use the power function, which allows us to calculate the exponents of any number. So I'll use powers of 2, so 2 to the power of this cell, and then I'll just copy this formula likewise across to all the cells. So now that our board is filled in with all the powers of 2, I'm going to come here to our first tab and calculate for each cell based on this actual board on the left. If the cell in the board has any value, if there's a peg in there, then we're going to set it equal to our power of 2 from the other tab. And if it's empty, we'll just keep it at 0. That's what that formula says, right? So you see as I put in a peg here using the letter O to represent a peg, the value changes from 0, which is a dash, to 1, which is 2 to the 0th power. And then I'm just going to copy this formula again to all of the cells on our game board. So now you see as I put pegs in individual locations, I put the peg here in our board, it gets the value of 4. I put a peg here, and it gets a value of 128. Okay, so that board will now take all the powers of 2. Now I just need to do one more formula here to sum up all of the values in our integer calculator board. And once we've done that, if we set up this game board to match what we have on our screen on the right, you'll see that our integer value is 1,208,615,568. And if I scrub over, that exactly matches the calculation here. So we've quickly prototyped something that can calculate the integer values. We can also do the binary representation of this. So I'll come here and I'll do a new formula. If on our game board, we'll say this time, if the cell is empty, so if equals, and then double quotes, and we'll make empty equal to the string 0, and then if there is something there, we'll make it equal to the string 1. So that's how we'll get our 0s and 1s for binary. And again, we'll just copy that formula into all of the cells. Okay, and now what we're going to do is use a string concatenation to basically build our bit field. So we'll do the string in this first cell and ampersand the string in this second cell, and just keep going like that to keep adding each of these values to the end of the string, and do that for all of the cells. And at the end, our formula gives us our bit field. And you can see these match exactly. So there's a quick tool to generate Genius Square bit fields. Fantastic. Now we know how to use bit fields to model games of the Genius Square. This is really the fundamental data structure that we'll be using in our solution of the problem. So in the next episode, part 4, we'll actually be putting this all together and creating some algorithms that work on these data structures to actually solve the problem. So we mentioned earlier that there's a giveaway, and throughout this episode we've been using boxes to represent bits. Well, our giveaway is actually very serendipitous with this. It's for a company called BitsBox. Now BitsBox is a subscription service that sends out box once a month, and it's a perfect kit that's used to help teach children age 6 to 12 fundamental coding techniques. So if you're interested in entering the giveaway, all you have to do is share the social media post for this video in either Facebook or Twitter. And as an added bonus, if you find the Easter eggs, remember there were 2 pie Easter eggs hidden in the video. If you find either one of them, you will get 50 entries instead of 1. And if you find both of them, you'll get 100. So if you really want to increase your chances to win, keep an eye out for those Easter eggs. For additional details on how to get your chance to win the giveaway of the BitsBox, just see the description of this video below. Keep learning, stay safe, and until we see each other again, keep taming irrationality bit by bit.